Okay, so I was asked by a student for a little bit of help, and they were saying that they're having trouble balancing chemical reactions that contain brackets. So in my mind, there are two types of balancing when you see brackets, or not only brackets, but polyatomics, right? Because that's where we get the brackets. Atomic ions. So excuse any background noise, because I'll probably delete the video in a few days. But so the first type is where the polyatomic ion remains whole on both sides. So it's not split up. You can see that we have a polyatomic ion here. Notice there's no brackets, but it's still a polyatomic ion. And we have that exact same polyatomic ion there. So it exists on the left and it still exists on the right in its exact same form. It's really important that it's the exact same form because it's pretty easy for these numbers to switch up, and that's something that's easy to overlook. So make sure that it's the exact same number. This is, in my opinion, the easier type of balancing problem. We have a second type of balancing problem where instead the polyatomic ion gets broken apart. As you can see from my example here, on the left we have SO4, but on the right it's now SO3. So it was broken up into this right here, and some of those oxygens were put in, or some of the oxygen was put into the oxygen gas molecule. So two different types. This one I feel is easier, and this one can get complicated. Okay, so now this particular student prefers to use visual representations when balancing. And so that's how I'm going to walk through this tutorial, because really I'm making this for them. So what you should notice is that I have already put my first molecules down. So we have an atom of lead, we have a molecule with 3 hydrogen and 1 phosphate, we have a hydrogen gas molecule here, and our lead phosphate here. So there's 3 lead in red and 2 phosphates. And I know this isn't correct in terms of our molecular models, but for visual representation it'll do for now. So the first thing you want to do is balance the metals. So that's what we're going. In this case though, our metal is all by itself, which means it's super easy to balance. We can save that till the end, or you could add a 3 now, it doesn't really matter. We might end up having to change that 3. So notice that my phosphates act as one big group. If I wanted to, I could zoom in there and draw, oops-a-daisy, and draw my phosphorus and my oxygen, but I don't need to, because I know that it's all together over here and it's still together over here, so I can pretend like it's one big group. So that's why I use the gray blob. In this way, you would solve these balancing problems the same as pretty much any other problem without the polyatomic ions. And that is by adding your molecules. So I see that I need another phosphate group over here, so I'm going to draw that. And whenever I see a phosphate, I'm going to get 3 hydrogen. So there's that. And now we have equal number of phosphates on the left-hand side and the right-hand side. All that's left to balance is the lead, which I've drawn. I've put a coefficient of 3. And I actually forgot to put a coefficient of 2 here because we have 1 and 2, 1, 2, 3. And now all that's left to balance is our hydrogen, and I need a total of 6. So I'm going to go ahead and make sure there's 6 hydrogen, and that leaves us with 1, 2, 3 molecules. So I'm going to put a 3 in front. And that's should be balanced. Double check my work, but should be okay. So now let's try that problem from above. This is gonna be a doozy, I can already tell. So this one is harder than your typical problem, but we're gonna work through it anyhow. And all it's gonna take is a bit of persistence, okay? That's what I find with a lot of balancing problems. Sometimes it just takes a bit of persistence. So in this case, our polyatomic ions, which are our sulfate and our sulfite, are different. They're not the same. So they cannot be treated as the same. They have to be treated differently. I'm going to draw lead again over here, and sulfur can be green, and we apparently have 4 oxygen. Ooh, this is going to be a brutal one, I can tell. Okay, sulfur is still green, and oxygen can be blue. And so hopefully that's clear. Maybe I'll put a legend just so that we don't forget. So lead is red, sulfur is green, and oxygen is blue. So what's the issue? The issue is this strange number of oxygen, okay? Over here, currently, it's 5 to 4, which means somehow we need this to be an even number, okay? That's sort of the thought processes that you should be starting to work through, which means this one right here is already an even number. So when we end, this has to be an even number, okay? I don't know what it is yet, but it's going to have to be even. The good news is that these numbers are our lead and our sulfur are already pretty close together, so there's no extra complication there. And what I'm going to do is I'm going to just start building in the way that I've talked about. So on the left-hand side, we're short on oxygen, so I'm going to redo my molecule. And currently we have A2, and we're going to keep a running tally of that. So now I know that my sulfur and lead are out of whack, so I'm going to copy that over. We now have 8 oxygen on the left, if you count 4 and 4, and we have, is that 8 oxygen on the right already? That was easier than I thought. Look at that, I was overcomplicating the problem. I thought we were going to get into the 5s or 10s area. So yeah, point is, you basically approach the problems the exact same way as you've already been doing. You just have to be careful about whether or not you're sort of labeling this phosphate group as one blob, or are you labeling it as multiple blobs. Just so you know, you can use this method, you can break it apart to solve these problems. So this method works every time. The second method, if you feel that's safer for you to do, if you can do it consistently and reliably, then that's great. Just do whatever works for you, okay? Good luck.